Here's an example rolling mill problem. A 300 millimeter wide strip, 25 millimeter thick, is fed through a rolling mill with two powered rolls, each with a radius of 250 millimeters. The workpiece thickness is to be reduced to 22 millimeters in one pass at a roll speed of 50 revolutions per minute. The material flow stress is defined by K equals 275 megapascals and N equals 0.15. The coefficient of friction is 0.12. A, is there enough friction to pull the workpiece through? B, if so, calculate roll force, torque, and horsepower. So here's what we're looking at in this problem. We have the workpiece approaching the rolls, and the rolls have a radius of 250 millimeters. The workpiece is to be reduced to 22 millimeters. It starts out as 25 millimeters. So the first thing we can calculate then is the draft. That's in millimeters. That's D equals the original height or thickness, 25 minus 22, so that's 3 millimeters. Second thing, the maximum possible draft, which is defined by the roll radius and the coefficient of friction. Use the equation R times U squared. So that's 250 times 0.12 squared, and that's 3.6 millimeters. So our first answer is, since 3.6 is greater than 3, then yes, this rolling operation is possible. B, if so, calculate the roll force, torque, and horsepower. To calculate the roll force, we need to know the contact length, and that is defined by the equation L equals square root of R over D. Square root of R times D. From the small angle theory, L equals the square root of R times D. So to find this contact length, the square root of 250 millimeters times 3 millimeters, which gives us 27.4 millimeters. The second thing that we need to know is the true strain, epsilon, and that equals the natural log of the original thickness or height. So we're using an H, so let's stick with an H, equals natural log of 25 over 22. That tells us the amount of strain in our operation. That's 0.128. The third thing we need to know is the flow stress. There's a equation that we have for flow stress. It says sigma F equals K times strain to the N power. It's the strain we just solved for over 1 plus N. And the K was given up here, 275. That's going to be the units that come out of this equation. 275 MPa times 0.128 to the N power, which is 0.15 over 1 plus 0.15. Do that math and you get 175.7 megapascals for the roll force. F sub R equals sigma F times W, the width, times the length. So basically what is that? That's the flow stress times the area. It's going to give us our roll force. That's 175.7 megapascals times 300 millimeters. That's the roll width times 27.4 millimeters. That's our contact length, and that equals 1.44 meganewtons. Now we have what we need to calculate the torque. That's the force times the contact length divided by 2. So that's 1.44 meganewtons times 0.274. That's 27.4 millimeters. So it's 0.274 meters. So that's 12.4. Let's stay in millimeters. 27.4 millimeters divided by 2. So that's 19.8 kilonewton meters. So then, because of that amount of torque, here's how much power we have to put in. The equation for power from torque is 2 pi NFL. N is the RPM, or the rotations, revolutions per minute. 2 pi. We said this is going at 50 revolutions per minute. So 50 rev per minute times the force, 1.44 meganewtons, times 0.0274 meter roll, length, contact length, and that gives us 12.4 meganewton meters per minute. Now to convert that to seconds for minutes. We take 12.4 meganewton meters per minute. We want to cancel minutes. So we're going to divide by 60 seconds. We're going to get rid of meganewtons because that's 1,000 kilonewtons. So we get 207 kilonewton meters per second. A newton meter per second is 207 joules per second, which equals 207 watts. And then 1 horsepower equals 745.7 watts. So we take that 207 watts times 1 horsepower over 745.7 watts, and we get 278 horsepower. This was supposed to be kilojoules per second and kilowatts. So 207,000 watts, 207,000. Because that's kilowatts, we have to change that's 0.745 kilowatts per horsepower. And so the result of 207 kilowatts divided by 0.7457 is 278 horsepower. That's how much power I need to drive these rolls to run this rolling mill operation.